As Itai said, I'm Marc Miskin. I'm a postdoc here at Cornell. And I can't imagine two better introduction talks for what I'm going to tell you about today. On the one hand, Jiwoon just finished his talk by talking about how if you work with atomically thin membranes as a folding material, you can pack an enormous amount of stuff into deployable systems that you can send out. And on the other hand, Robert showed us about all these fantastic, all these fantastic things that you can go and build with origami. And I have one criticism for your talk, which is very minor, and that's that everything in your talk was way too big. Except the DNA, that was too small. So what I want to talk about are deployable machines, as Jiwoon said, about on the size of cells. And that's really the goal of what I work on here at Cornell, is building machines at that length scale. And to specify why, I'm going to go back to something Paul talked about earlier, and that's sort of an idea like a Moore's law for machines. So in microelectronics, two of the key ideas are miniaturization and integration. You get a lot of circuits that are individually modular, and you pack them together, and then you figure out how to shrink it down. So there's millions of examples of how that's cool. My favorite is this one. It's the Intel 4004. It was made in 1971, and in 1971 it was about 1 millimeter square big. It's about the size of a pen head. If I made it today at CNF without breaking too much of a sweat, I could make this amazing thing at 10 microns, the size of a red blood cell. And so that's the progress of that technology. And so the question is, well, can we apply these ideas to machines? And you might say, well, you know, in some sense we have, right? There's MEMS. This is from Sandia. It's a ratchet actuator. It's an enormously complicated piece of technology to produce rotational motion. It's got these latches and these little mechanisms inside of it. But this is huge. This is still 100 microns big, right? If I put that circuit board on it, it would sit there in the center. Everyone see the little dot that just suddenly showed up? That's how big they would be compared to each other. And so it's a cool machine, but it's not really in the spirit of what it is that we want to do. Really what we want are mechanical elements that can be scaled up or down arbitrarily in size. And we want to do this with maintaining this concept of integration. It's got to be compatible with other nanotechnologies, say silicon, DNA, information processing, etc. And last, we want these things to be deployable. This lives on a substrate. It's stuck on this piece of silicon. I want them like cells floating around in the body doing their stuff. Sensing, reporting information, etc. And so our group at Cornell has really been committed to this idea, which is to leave behind kind of the MEMS paradigm and focus on this folding approach of going from 2D into 3D. And what we see is that origami with atomic membranes is a clear mechanism that we think we've identified for building kind of these autonomous machines at the size of cells. And I want to show you up front that that's true. So here's a tetrahedron. It's going to be a tetrahedron. It's got these 3 panels on it. And the scale bar here is 15 microns, so that's about the size of that circuit piece I showed you on the previous slide. And this is a machine that I made. It's able to fold up reversibly, back and forth. It's deployed. It's floating in solution. And this talk is going to tell you largely about how we came to build this object, what it's made of, why it works. But I just want you to get the impression that this video is real time. So this is happening at about 100 milliseconds to fold. And the scale bar is 15 microns again, so this is on the order of a red blood cell in size. Okay, so that's how this talk ends, but let me zoom back out. Here's the fundamental idea again, though, right? And that's this one that Robert really made a good job of pointing out, and that's that origami is scalable, right? If you build an object at one size scale, the mechanics are such that you can shrink everything down and it will still just work. That's very different than a set of gears where friction becomes more important as you get smaller. Here you can just miniaturize, and that's very powerful, right? The other thing that's cool is these things on the left, you know, they're origami and they're objects, but they're largely static structures. And as Robert also told us, origami is a fantastic way to make mechanisms. And if you can make mechanisms, you can make robots. So here are 2 examples. On the left is Rob Wood's origami robot. This thing folds itself up, walks away. On the right is Danielle Russ's little magnetic robot. You can kind of guide the thing with magnetic fields. But these were both made with self-folding sheets that assembled themselves. And so the question you can kind of ask is, if this is really scalable, what do we need to do to scale this down to cellular dimensions, right? If I can really just miniaturize the thing, then what do I have to do to bring this thing down to the size scale that we see in biology? And the answer is this. It kind of relates to Jiwoon's point. If you want micron-sized robots, you should use atomically thin paper. And the reason is pretty simple, and it has to do with this wish list of things that your origami robot has to have. One is that everything basically boils down to the actuators, the little points where the folding is taking place. The rest of the object is by and large flat, And so from a materials point of view, you don't have to worry too much about what's going on here. You really have to worry about what's going on there. And the actuator has to satisfy this list of demands, right? One is that I want cells, so micron-sized folds. Two is I want everything to be elastic because I want this robot to be reversible. I want to be able to fold and unfold it. Three, and this is a tricky one, is I need conductivity, right? Because if I want to have circuits or functional elements embedded on this, then I need to be able to send signals across it. This is one Robert made a great job pointing out. I need high stiffness because I want large force, right? If I'm going to embed some heavy, chunky thing on this, something functional, I want to be able to move it without having to think too hard about how that's going to work. And the last two, right, is compatibility with semiconductor processes so I can maintain this integration stronghold. And finally, I want high surface temperature and high chemical stability. I don't want this thing that's going to disintegrate if it goes into acid or it's going to burn in air or whatever. High stability, that's key. And what's beautiful is that atomic membranes, in particular graphene, give you all of these properties. Every single one of them. Graphene's the stiffest material known to man, the most conductive. It's thin enough to fold to nanometer radii of curvature. It easily hits all of these marks. And so all you really need to do is make an actuator out of this, and then you're on your path. Okay, so how do we do that? How do we build the graphene actuator? Well, it's going to be the world's thinnest actuator, and this is how you do it. To build any bending actuator is really pretty simple. You take your one material of choice, and then you layer it with another one, and find a way to introduce a strain difference between the two. So let's say this one wants to expand and that one wants to contract. Well, they're going to bend in order to satisfy the two geometric, the fact that one wants to be longer. And the trick here now is, okay, well, if we pick graphene as one of the materials, really it boils down to, well, what do I layer it with to make this into the best possible actuator for the job? And you can answer that. So what we want to do is we want to maximize the force output for a given radius of curvature so we can solve this low energy problem. And that implies that we want to maximize the flexural rigidity, the bending rigidity of our plate. So for a given material, that's given by the modulus times the thickness of it cubed. Now we have a constraint here, which is that we don't want the actuator to fracture. Everything's got to be elastic. So that means that we need the strain inside the layer, the thickness divided by the radius of curvature, to be less than the fracture strain for a given material. And you can combine these two equations, and it tells you that really the thing you want to maximize is the product of the radius curvature cubed, but this is just given to us. So the material thing we want to maximize is the fracture strength cubed times divided by the Young's modulus squared. So you can go and dig out all the materials known to man, you plot these two things next to each other, and you put this little metric in. So good materials for the actuators are this point of the material space, bad materials for actuators are on that side of the space. And what jumps out at you immediately is graphene is way over here. It's off the charts as far as, it's in its own little category. So this is a fantastic material for working with. And now we're left with just picking between two other things for a second layer in the actuator, and that's between ceramics, so things like glasses, and elastomers, things like hydrogels. Now, if we put in one extra constraint, which is that the graphene can't fracture, it also has to be elastic, then we need materials that live below the fracture strain for graphene. And that essentially rules out elastomers and leaves us with one set of materials that are going to give us our optimal choice, ceramics, so glass. And so for our first prototype, that's what we built. We made graphene layered with 2 nanometers of glass. Here it is, this beautiful cross-sectional TEM that David's group helped us with. What you see here is a layer of aluminum. This is aluminum oxide. It's a release layer. We etch it out with hydrochloric acid to release our devices. Here's this 2 nanometer thick layer of silicon dioxide that we grew. And on top of that, this is graphitic carbon sitting on top. That's the graphene layer capping off our little actuator. So, okay, so this is what we're working with in cross-section. First question is, does it work? And the answer is yes, it does. It works in several different ways, but probably the simplest thing you could check is if this thing behaves like a bimetallic strip. Right? You have 2 materials. They have different thermal expansion coefficients. So what does it do when you heat it? So what we did is we picked up one of these devices. We're holding it with a tungsten probe. And I zapped the tungsten probe with a laser, and that heats the probe. The heat's conducted into the bimorph, and lo and behold, the thing bends. So it just curls itself up. In this case, it's the graphene is contracting relative to the glass, and you get a curvature that's proportional to the temperature as the thing goes. So minor victory, we've done it, we've made the world's thinnest bimorph, this thing works. And in fact, you can go and you can quantify this, and you find some interesting things. One is it is in fact linear. The relative mismatch in thermal expansions is about what you would expect. It's somewhere around 10 to the minus 6 in strain per Kelvin, so that's typical for hard materials like glass and graphene. The other thing that's amazing is even up here at about 165 C, so we can locally superheat the water because we're using a laser, we're still way below the fracture threshold for the glass or the graphene. So this thing's still behaving elastically even in this regime, and this data set is reversible forwards and backwards. But by and large, right, this is sort of the simplest thing that you could imagine doing. It's just sort of a proof of concept, except there's this one little thing, which is that this curvature down here is not zero, even at room temperature. There's this finite value. And so we started to ask, well, could we control this? What sets this? Is this a mechanism for actuation? And it turns out it is. You can do it, but you have to know something about this first, which we didn't know, but the Corning people knew, that you have to know how Gorilla Glass works. And I'll tell you about that briefly, just as a mechanism, and then I'm going to tell you about how we use this technology as an actuator. So Gorilla Glass works the following. One is you take a piece of glass that has inside of it little sodium ions, and you jam the glass into molten potassium salt. So just molten potassium. And when you do that, these ions, the sodium and the potassium, can exchange with one another. There's no reason that the sodium has to live in the glass. Some of them diffuse out, some of the potassium diffuse in, and you have a reaction that eventually goes to equilibrium. Now, that's all well and good, but there's they've switched. And that's all well and good, but there's a catch here, and that's that potassium ions are larger than sodium by a significant amount. And so once they've exchanged, they start to swell the glass, and that leads to stress inside of the layer. In short, the glass swells to accommodate the larger sodium. So okay, so that's how Gorilla Glass works. What does that have to do with the graphene glass bimorph? Well, you might not think that molten potassium and water have anything in common, and you'd be right, by and large. But there is one thing that they do have in common, surprisingly so, and that's that they're both electrolyte media. And in fact, more than that, acid molecules, so hydronium and water, are almost exactly the same size as potassium. Like, the ionic radius is amazingly close, like 2% different. And so that means that this is again a mechanism that exists that can swell the glass when associated, except it would happen in water at room temperature. And this also implies that this is a mechanism that can be controlled, right? If before I had the case that I pushed out the sodium by putting in the potassium, well, here if the swelling is due to the acid molecules, I could drive them out by putting sodium back into the solution. And so that's what we did. Here we just raised the pH by adding sodium hydroxide, so simultaneously we're decreasing the amount of acid molecules as we're increasing the amount of sodium, and lo and behold, that finite curvature from the previous graph drops off at a critical value of a pH around 9. You can work out, again, if this goes to chemical equilibrium and the strain is really due to the acid molecules, that gives you a functional form for the strain, and you can, from there, get a best fit to the line and kind of come to the conclusion you understand this mechanism reasonably well. What's neat is that this then tells you the curvature as a function of all the relevant environmental conditions, the pH, the PNA, and also the temperature combined with the previous graph. So let's jump back for a minute. This is our actuator. This is roughly how it works. How are we doing with this target properties list, right? Well, we're actually doing quite well. Right? One is this is clearly compatible with the semiconductor process. I made this thing in a clean room with conventional tools. I just showed you two graphs that showed you 165 degrees roughly in temperature and a chemical stability over 13 orders of magnitude in acid concentration, so that's also pretty good. All these bends, these are all micron scale. Here this is about 7 microns or so that box is ticked. Everything's reversible and elastic. It all goes forwards and backwards. And I engineered the thing to have the highest possible stiffness given my material choice, so that box is ticked too. There's really actually only one box left, and that's this one about conductivity. So that's what we checked next. The experiment here is pretty simple. You take a graphene glass bimorph, and you want to pass a current across it while it's bending. See what it does. So this is what we built. It's a source, a drain, and then the current passes through the bent bimorph, so you can measure how much current flows as a function of voltage. Here's the actual experiment. You can see source, drain. This fuzzy image in here is the bimorph bending out of the plane. And when you pass current across it, you can measure the current that flows as a function of voltage. And from there, you can measure the effective resistance along this joint. What's interesting is that if you extrapolate from these measurements, you would find that if you built a micron-sized device, each joint would be equivalent of about a 100 ohm resistor. So that's a livable number. You really could build components where you would have circuits linked across these individual elements. If you're wondering how do you know that the current is actually passing through the graphene and not just through the water, you can do things like gate the electrolyte relative to or gate the source drain relative to the electrolyte. Graphene gives you a transistor-like response. You're not going to get this from water alone, so this is just to prove to you that we are in fact measuring what we think we are, that the current is in fact flowing through the graphene. So okay, so our checklist is done. We have this bimorph actuator that really does hit all the marks that we want for building these small deployable systems with complex payloads. But these are still just bends, right? They're not folds. We haven't actually made a fold yet. So that's what we have to go and do next. And the way you do it is actually quite simple. As Robert said, one of the key ideas is you just vary the flexibility between the two layers to make a panel that's much stiffer than the joint. So what we did is we patterned enormously thick layers of polymer. They're 2 microns, they're about 1 million times thicker than the graphene glass bimorph. And as a consequence, they're much thicker. They're much more stiff. And so the bimorph can't bend here, but it can bend here. And when you release it, the device will, in principle, fold up. Here's a micrograph of exactly what I just showed you. This is a bimorph bent at 90 degrees holding a pad up. And here's my probe tip again. I'm coming in and just poking on the hinge. And you can see that this little guy deforms elastically under the load from the probe tip and then just goes back to its rest angle position. Now what's cool is that this pad, right, is quite heavy. It's much, much thicker than the bimorph, but the bimorph is able to easily lift this object. And in fact, if you work it out, this is the weight equivalent of roughly 500 nanometers of silicon. So the force output here is actually large enough that you could seriously think about a wide range of very serious functional payloads. But let's say that you don't just want to bend them, you actually want to build complex stuff. How do you go and do that? Well, let's say you have a target shape of a cube. Okay, well, we have this data that tells us the radius of curvature for each of the bimorphs as a function of the environmental conditions. So from there, it's actually just a straightforward bit of algebra, a little high school geometry to figure out what the lengths of pads should be such that the angle, that if it wants to wrap to a curvature of a given value, how far apart should these be so that the total angle between the two pads has the desired, let's say, 90 degrees here. And in fact, you can go ahead and build it and set the thing free into the real world, and it works. But you're not just restricted to building one shape or even one shape at a time. In fact, because it's lithography, you can build anything that you want. Since I'm picking on Robert particularly, can you look in that and tell me what do you roughly see?
Well, I see a wafer and a little dark rectangle.
Yeah.
And a whole slew of small rectangles.
You see the little rectangles, yeah. Those are these. So every one of those little rectangles that's repeated is this entire unit, right? So on that, there's roughly 10,000, 100,000 devices that have all been fabricated, the variety of different patterns. Each of the little units arrayed here holds, about 10 by 10 or so of these devices. And you can go ahead and you can release these and etch out that aluminum layer, the shiny mirror layer on the bottom, and lo and behold, they work. So here's a variety of the objects that are on that chip that's being passed around. We can make little tetrahedron like the one I showed you at the start of the talk. We can make helices where you can program the pitch angle. This is kind of fun if you want to build an antenna, especially a tiny antenna. We can build high angle folds, so a book where you fold two sides on top of each other and latches that clasp the thing shut. We can play with some of the constraints from rigid origami to make mountain valley folds, even though we can only actuate things one way. You can ask me about that later if you're really interested. And of course, we can make the cube. And the key thing to remember is that not only can we make all of these objects, and not only can we make them about a factor of 10 smaller than anybody else for this type of a folding mechanism, but every one of these is elastic. Every one of them survives at 140-degree temperature range, 13 decades in acid concentration. And they can all support embedded payloads like electronics through the conductivity of this functional layer of graphene. And so that's the story of how we came to make this little 15-micron object that's responding to acid and base changes. That's what's driving this mechanism. That's also, by the way, why this is so fast, right? This film is only a nanometer thick. So one of the other cool things about working at this size scale is not only can you lug around heavy functional payloads, but you can move them very quickly because the time it takes for those acid molecules to diffuse in and out of 2 nanometers is very, very short. So that's where we're at. I just want to take the last 2 minutes and tell you a little bit about where we're going. The first is sort of the story about a toolkit for cell-sized robotics, right? And that's graphene glass is a prototype. It's one of a class of actuators that you can build. And there's a wide variety of other hard materials that will give you most of the functional aspects I talked about that you can also make in a clean room. So already in our toolkit, I showed you silicon dioxide and graphene. We also have now hafnium dioxide, DNA, and platinum. And these are things that we're developing right now. So here's graphene glass. It's temperature and pH responsive. We also have platinum glass, which is voltage responsive. If you dial up a voltage on the probe tip, you can curl and uncurl an actuator. We've recently developed DNA glass. So here's one of these bimorphs. You're looking at a fluorescence micrograph of DNA bound to a glass unit. If you add in the complementary pair for hybridization, you can make this thing expand and contract. And each of these brings you these new kinds of cool mechanisms for sensing and actuation. And the last point about this is all of these are really the tip of the iceberg, right? The curvature limit for these is between 10 to 100 nanometers, as Ji-Woon pointed out. That's the tightest radius of curvature you could make. We're still 2 orders of magnitude above that. So there really is this kind of Moore's law thing living here, that we can scale this down another 2 decades if we want. And finally, I want to jump back to this other point. So this is sort of a wide variety of stuff, and a lot of this talks about miniaturization. But there's this other side about integration, right? They really have all these properties. What else can you put on them or in them? Well, let's jump back out to this circuit board, this microprocessor. At 10 by 10 microns to scale, it would look like this, right? These would be the tetrahedron I showed you. That's the Intel 4004, which would mean that this object would fit right onto one of those panels. Or here's the world record for RFID. It's about 50 by 50 microns, which means it would exactly fit on one of the faces of this box. So combined with the toolkit from the semiconductor industry, you can really start to think about building a really amazing platform for building microelectronics that are deployable and again comparable in size to biological organisms. So here's a heart cell. Michael Reynolds took this micrograph. It's about 10 by 100 microns. Here's our little helix. It's about the same aspect ratio. If you want to put it into a sentence, you could say, using conventional lithography, you could build devices that could each carry more processing power than Voyager, but remain small enough for injection into the body. So here are kind of our takeaway points. We've developed a platform that, if I want to sum it up, we've developed a platform around self-folding sheets with the thinnest possible materials, tens of atoms thick. And the benefit of this, of working at the scale, is that you now have enough force, flexibility, and functional properties to really think about building complex deployed systems that are system-size, micron scale, made from nanometer scale parts. So with that, I'm going to take questions. Did you pass that around? Oh,
Yeah.
Okay.
Yeah. How fast can you manufacture this?
Pretty fast. I mean, so probably, we haven't optimized the speed for starters, right? So if I want to make the graphene glass bimorph, it's 2 days for me to go from start to finish. Now, one of the intermediate steps is because we're very cautious about removing the photoresist as a middle ground. And if you could eliminate that overnight soak, you could do it in 6 hours. Again, I think if you automated it, you could really crank these things out.
Do you have materials in mind from which you can get both mountain and valley?
Yes, you should have talked to Barish. So one of the things we've been exploring has been, glass is a pretty powerful toolkit, especially when you can vary the chemical composition down to atom precision. And roughly speaking, we can do that. So one of the things that Barish has a poster on, you should absolutely ask him about it, has been making multi-layer glass stacks. So we retain all the functional things I told you about, the high force output, fast actuation, et cetera, but now with kind of the control that you see in the polymer type stuff, right? Tri-layer designs, bilayer folding, all the good origami design that's gone into polymers, we just want to push that right into this other platform. The other thing that's fun, by the way, which we're pursuing too, is the pH transition mechanism is programmable. It depends on the chemical composition of the glass. So you can envision mechanisms for sequential folding as well here, in addition to mountain valley, which is beyond, I think, polymers in some ways. You pick.
Can you make this time not to hold a liquid inside and use it for encapsulation?
Not yet. So as you can kind of tell, the joint tolerances here aren't great, right? And getting it to be more or less atomically close it would be a bit of a trick with this mechanism. You really need a glue. Now, we've talked about it. Like once you have DNA and you can put that on a surface, you could think about building things that self-seal, et cetera. But yeah, no, the liquid encapsulation is still hard for us, but I think it's a goal for sure.
One of your first slides, you had constraints of materials based on modulus and fractal.
Yep.
I think those constraints that you're using from looking them up in the literature don't necessarily apply to what you're trying to use. So if you measure polymers in the bulk, their behavior is very different when you're constrained to a thin
Yep.
film. And if you're using thin films that are in the hundreds of nanometers thick or thinner, they're going to have very different properties, both for modulus and fracture.
You are absolutely right.
So I think you have a much bigger space in materials.
The graph I showed you is for MEMS. So you're totally right. If I took out Ashby's textbook and I just opened a mechanical engineering design book and I plugged in the numbers, I would find that glass would be a terrible choice because its fracture modulus, for a macroscopic value, is nowhere near the nanometer thick value. The graph that I showed you is one I made using literature values for thin films. So in the MEMS case, you're 100% correct. You really have to correct for it. And in polymers, it's a little murky too, right? Because you often wind up with the design projection is that, well, it should be, let's say, 10 nanometers thick to make a good bimorph. Well, what number do you use when you're at the polymer pitch?
In a much bigger space, comparing graphene versus graphite, graphene is very thin and has very different property sets than graphite, for example. I think there's others that will relax the space a lot, so you have more materials to select from.
That may be true. Like I say, though, we both agree that there is a version of this graph that you can make using microscale parameters. Yeah.
I think, again, we're running, why don't we end it here? Let's thank Mark again.